Hello, everyone. Evgeny is here. Welcome to VSA Online, and it's my special pleasure to welcome Eilene Tomkins-Flanagan and Mary Kelly from Carleton University, who jointly will give a talk with this catchy name, Hey Painty, we did it again. And it will be about hyperdimensional implementation of Lisp, roughly speaking. And I also want to say that this presentation is collocated with the introductory class on hyperdimensional computing, as I understood, as I
That's
learned.
correct.
And I'm very happy to see the rising number of live um, attending people. So without any further delay, Eileen, Mary, floor is yours.
Thank you. Um, so this is a talk that we originally presented at ICCM this past year. I meant to tailor it for VSA Online, but due to the complications of the first week of class, I didn't really get the chance to. But that's okay, because we can go into a lot more depth and detail here. So even for those of you, if anyone was at ICCM, we'll be able to cover some more interesting stuff. Um, what we're talking about here is we are going to briefly go over vector symbolic Lisp. However, the recent work that we've done does not directly concern Lisp, but a functional programming language called LLFPL with some interesting implications, as well as a very interesting type encoding. So let's get started with framing. Going to go over motivation for a bit, hopefully not too long. Mary's going to cover some of the more technical details, and I'll cover discussion wrap-up questions. Okay. So a really interesting observation, and kind of an obscure observation in psychophysics is well, maybe not that obscure, because it was taken very seriously by Herbert Simon, um, is that as humans gain expertise, of course, there are response time decays, but it decays in a very sort of well-behaved way. However, there was considerable debate for a number of decades over whether it decayed according to a power law, or according to a power decay, or according to an exponential decay. Um, Simon believed that he'd concluded, or that it was concluded fairly thoroughly, and that this power decay could be elevated to the status of a psychophysical law. However, some work initiated by Heathcote, Brown, Mewhort, and eventually some others. I think there was one other person on that first paper, starting in 2000, but the most recent paper in that series was in 2018, found that individual subjects sometimes learn according to a power decay and sometimes learn according to an exponential decay. The reason why this is quite an interesting result is that Simon used it to validate his theory of learning as search. He interpreted it as a confirmation of his search-based learning theories, or heuristic search-based learning theories in particular. Um, because the particular the characteristic function of this learning decay bears quite strongly on what kind of search strategy people are using as they learn to solve a problem more efficiently. And this may be more visible if I replot these curves first in log coordinates, and if I replot assuming that the sort of optimal performance is our zero line, replotting with the optimal performance at the zero line, we can see very clearly that these are really distinct characteristic functions that show really different information gain properties. So importantly, that first graph shows on some particular task that one subject was learning according to an exponential decay, but this varies between subjects and can vary across tasks and even within tasks. However, the point here is that humans sometimes learn according to this exponential decay curve. And that's really relevant because this power decay is exactly the decay that we see in transformer neural network models. The so-called scaling laws of transformer neural networks, when you give them more resources, more time, more compute, more parameters, they follow they follow an exponent, or they follow a power decay curve. This is even visible in test time compute, kind of. They have a more severe efficiency drop off. But it seems that humans are able to do something radically more efficient. To sort of paraphrase the 2018 paper, um, the um, the power decay is indicative of search through a space of possible um, methods of solving a problem that that increases skill with decreasing efficiency, whereas the exponential decay, the exponential decay shows a constant efficiency. So humans are at least able to do something that is radically more efficient than the power decay. Um, what's interesting about this is that it seems to be actually quite important that humans can acquire, can learn to acquire skill quite efficiently. We see that this power decay function, although it's touted as one of the properties that makes transformer neural networks so powerful, um, the scaling law still does not save these networks from a really severe case of diminishing returns on some tasks. You can see here in the top right corner, this is a task called the ARC-AGI task, which is a sort of IQ-like task that's designed to be really easy for humans to demonstrate the flexibility of human intelligence against current AI models. You can see here human performance relative to cost, which is a good proxy for computing resources, is quite good. Like these tasks are really, really easy for people, and it's really, really cheap to people to do these tasks because they don't require a whole lot of effort to do. However, all AI models, if you invest a lot of resources, like an exponential amount of resources, about 2,000 per query, you can almost reach human level performance, but at the cost of doing a whole bunch more computation than people are clearly doing at this task. You're boiling liters of water to perform it. Um, so and for the second version of the ArcAGI task that just came out this year, they're of course not doing well even a little. So this is really interesting because it seems as though human cognition is able to learn in a way that is radically more efficient than existing models. And the, and our thought on the matter was, what if they're learning in a way that's radically more efficient because they're able to, and this is part of Chalet's design for the task, because they're able to somehow take advantage of the structure of the task in order to more efficiently find solutions to the task problems. There's some really interesting sort of indicative research as to why we should believe this. But just to sort of set the stage, of course, we have Photo Impulation's really classic paper explaining why, in some cases, human cognition we should expect it to be absolutely dependent on what they called a combinatorial constituent structure of mental representations. And they propose at the tail end of this paper that we will need not an empiricist idea of learning that is like similar to end-to-end backpropagation, where they just learn from examples and sort of fitting the weights, but a rationalist learning theory that builds theories that try to represent the structure of the problem that we're trying to understand. And we have some good empirical reasons to believe that this might be true. This is a graph from some work that Stanislas Dehaan's group did, mostly borrowing on other people's research, but it shows that the cognitive load of performing certain tasks tracks very closely with the minimum length program that represents those tasks. We can think of this almost like building a theory that represents that parsimoniously represents the relevant degrees of freedom of the task. And they find that this model that expects this minimum descriptive program, they find that it fits better than other measures of information for these tasks. And part of the reason why we might want to believe that humans are really good at finding these programs is a theory, old AI theory in the grand scheme of things, although not that old if you really think about it, developed by Marcus Hutter, called ICSI, which relies on these minimum description length programs in order to build an optimal reinforcement learning agents. And what Hutter finds is that optimally rational, optimally goal-directed behavior is really, really trivial if you have an optimal representation of your world. That is, if you build the shortest length program that represents your world and is most likely to be a representation of your world, then it's really, really easy to behave in a goal-directed way effectively. So where this work is kind of tending towards is we want to ask, how can these representations exist in the brain, and how could they potentially be learned efficiently? Hutter's work, importantly, we don't have AGI right now because it's incomputable, and even if you finitely bound it, it is NP hard. So in order to get the kind of efficient learning that we want, we're going to have to change approaches considerably, so as to render it efficient, and that's sort of where this work is exploring. Okay, so we're going to start with talking about how we build these representations at all, and we're going to then move towards talking about our language that doesn't complete the picture, but trends towards learning them efficiently.
All right.
Yeah. Go ahead.
Should I go?
Yeah.
Okay. So all the line of argumentation so far, humans are much more efficient at learning and representing the world than the current state of the art in AI. And there's some reason to believe that simply making these models bigger and bigger and bigger, like the big AI companies like to do, isn't going to get us there. So we need a new approach. Chalet came up with the ArcAGI test, thinks that the approach is program synthesis. And this seems to align with this notion that we have some sort of optimal, efficient mental representations that allow us to represent the world and what procedures we need to enact on the world to solve problems that we run into. So in other words, mental representations need to include programs. Now, how do we make a mental representation include a program? Given that this is VSA Online, you might have some guesses where this is going. So we need also program search is a very can be very costly because programs, well, for example, there's the halting problem. A program might not ever stop. So let's say you come up with some program and you want to test it out to see if it solves your problem. You start the program, and then that might be it. That might be the rest of forever. So we actually want programs that are some way constrained so that we can actually tractably do program search to solve problems. This isn't really too much of a problem if we're thinking about the case of biological human beings. Human beings don't have infinite amount of time to consider a problem. Human beings are, for better or for worse, programs that do ultimately halt at some point. Fair enough. So we need to be able to represent programs and in a way that can be realized by either neural tissue or by artificial neural networks. And this means that these representations have to be distributed. They have to have propositional or logical content. So there's a technique that does really good at this, and it's called vector symbolic architectures. It might be familiar to some of you. And so that's the plan, is we're going to describe how to write programs using vector symbolic architectures, with the idea that this will be a useful tool for doing program synthesis AI systems. Can we encode arbitrary programs in a VSA? Yes, of course we can. We have a couple of papers out. This talk is kind of based on 3 different papers. They're not super searchable right now, but they are out in the proceedings. This one is in the ICCM proceedings. We'll put it up on archive to make it a little bit more findable soon. But basically, we can, in fact, make a VSA a Turing machine. And lambda calculus, which is equivalent to a Turing machine, is just a subset of the Lisp 1.5. So we're just going to do Lisp 1.5, which is a very minimal set of functions that will be able to do anything a Turing machine can. So a quick definition of vector symbolic architectures. A vector symbolic architecture can be understood as an algebra. And it has these properties. It's got a product operation. It is closed under that product operation. So we take some vector v, and we have this product operation, which in some cases is convolution, some cases it's multiplication. It's some sort of binding operation that gives us that takes 2 vectors and produces another vector. We've got some sort of approximate inverse of the product, though in some VSAs it's an exact inverse. And then there's some way of selecting our atomic symbols from the space. Typically, they're randomly generated vectors. We have some cleanup memory system that allows representations to be corrected back to one of the canonical symbols. And we have some way of testing to see if 2 symbols or 2 vectors are similar to each other. Typically, vector symbolic architectures also include a permutation operation, which is a unary operator that transforms a vector into a different vector that's dissimilar to the original vector, but can be perfectly restored to the original vector by reversing the permutation.
Importantly, the reason why we're going over this broad definition here is because we're going to assert that all vector symbolic architectures, there's many, but they all either have or approximate these properties, but formalizing the core properties of vector symbolic architecture allow us to show that we can design a Turing-complete language for an arbitrary VSA.
So even though our implementation uses either holographic reduced representations or frequency domain holographic reduced representations, you can use any VSA to build this, really. All right, so Lisp is a famously extremely recursive language, and it's entirely based on lists. Lists are defined in terms of recursively in terms of there's the empty list nil, and then there is a head and a tail. The head is some piece of content that is stored in the list, and the tail is the rest of the list. And so then you recursively define a list as there's a thing, and then there's the tail, and the tail can be another list, and so on. And we can represent this pretty straightforwardly using a vector symbolic architecture. In this particular case, we have left convolved with, let's say V here is our head, plus right convolved with the tail, and then plus a token here that represents the fact that this is a list, so that you can quickly check this vector to check and make sure that it is actually a list. So this allows us to retrieve the value, retrieve a pointer at the tail of the list, and test whether or not a vector is a list. And this we can use the cons function in Lisp to construct lists. All right, so, and just kind of ignore the nil as conventional in Lisp representation. We need a lambda, some way of doing lambda expressions, which is to say some way of doing functions. Basically, it is a recursive substitution rule. If you have essentially no function, it's very simple. But essentially you do this substitution process. Yeah, I don't know. Say about this.
I can elaborate. So of course, in the lambda calculus in Lisp 1.5, we can very efficiently define arbitrary computation as a kind of string substitution. The important result in our first paper was that we managed to define string substitution entirely in terms of vector symbolic operations. So it shows that the VSA in and of itself can encode a Turing-complete language.
All right, thanks. So, all right. Now, we don't actually want Lisp. If we're trying to do program synthesis, Lisp is a great language for doing a quick demonstration because it's such a simple language. And if you're just trying to show a VSA can implement an arbitrary programming language, Lisp is a great place to start. But if we want to do a specific application, and that's program synthesis and an AI system that finds the right program to solve some problem efficiently, we want actually something much more constrained. We want a programming language that is actually only going to give us programs that we can tractably search over. And so to do this, we still want this class of programs to be as expressive as possible, but not actually Turing complete. Basically, this should allow us to further constrain the search for terms. So in typed languages, types constrain our search. So we're going to choose a typed language that expresses all and only the tractable programs. And to do that, we're going to use a special language called LLFPL, which is log linear. Is that correct? Or
light linear
functional programming language. All right. And
it comes out of the domain of linear programming languages, which are a particular tool used in formal logic.
And Eilene has named the particular programming language that we're going to use Doug, after Doug Newhart, who was a cognitive psychologist and computational cognitive modeler that Eilene and I both worked with and trained under. And partly this is because the acronym gets very, very long when you add extra letters to represent the fact that this is going to be a vector symbolic implementation of the language.
Already pretty bad.
Yeah, LLFPL is a little tough. All right. So I'm going to represent this using slot value encodings. And here's some of the here's basic definitions that define this language. We still have like a cons function, but we have some new stuff that's maybe, and a lambda function. We have some new stuff that's maybe not quite so common in computer languages. The main thing here is $, which is a currency that the language has to expend as it goes like as it basically does computations, and this limits the amount of recursion it can do and constrains it to polynomial time execution, which kind of solves, in a certain sense, the halting problem in that having given up being Turing complete, we have created a system that will halt because it'll run out of this sort of money thing, this dollar currency.
Although importantly, although we are paying in terms of expressivity, we're only paying in that we're restricting ourselves to the set of all traditionally considered useful programs. So it's not that bad of a restriction.
So the other thing is, in order to learn over a language, we want to have actually a space that we can traverse and optimize over. And that's kind of part of the benefit then of doing this as a vector symbolic architecture, is that we can define types, and these types have internal similarities to each other, and we can then learn over this space of types. These are going to be very detailed types. So they actually tell us a lot about the function that we're potentially executing. They're going to tell us both about kind of the inputs and outputs of the function, but also potentially internal properties of the function.
So our goal here is to take a very formal approach to constraint learning.
All right. And so the types are differentiable because they live on a continuous embedding space. They are analytically decodable from points on that space because they are vector symbolic in nature. And we have a memory system that can then resolve the points near types to the nearest types, so our cleanup memory. And spatially nearby types have similar structures because, again, these are the desirable properties that a vector symbolic architecture have. To do this, we use a particular type of encoding that is inspired by my earlier work, holographic declarative memory. So the thing that holographic declarative memory does is it uses permutations. So we can use permutations to represent a slot and then a vector to represent a value. And then combinations of like a set of slot values are convolved together. So let's consider an example. So we have some sort of function, and this is a very generic expression here. Essentially what we're saying is that there is little lollipop symbol is just a arrow symbol. Basically, it is a mapping from a domain to a codomain. And so a function takes input of some kind and produces output of some kind and maps between the two. So how do we want to represent this? Well, we can represent the type of this as a set of key value pairs. So we can say that the kind is a map, which is a generalization of the notion of a function. Its type is then defined by its domain, which is the space of things it takes as input and the space of things it produces as output. And then there's this level property, which ties into Doug being a constrained language. The level is constraining when this function essentially can be called. If you're past some kind of recursion depth or nested computation depth, you've run out of resources. You can't call this function. You have to stop. So to encode this representation, there's this set of slot value pairs or key value pairs. We're going to take the power set of this set of key value pairs, which we just do by we permute the vector representing the value by the slot, and then we convolve together or bind together the different slot value pairs or permuted values to get back the representation of this function's type.
Importantly, we use the power set of this type encoding because we are convolving all subsets of the set representation of the type, and then we're summing all of those results together. This is important in order to give us the final property, which is we can show analytically, although we don't in the paper, that types are going to be similar if their set encodings share subsets or different subsets with similar encodings.
All right. Yeah, and this allows us this partial similarity essentially, which helps make it learnable. All right, I'm going to turn it over to you. I think we only got a couple minutes left. Is that correct, David?
We have negative minutes left, but that's okay.
All right.
There's only one slide left, but here's where we're going with this. So first off, the reason why I use the phrase divide and conquer on this slide is that that is the kind of search strategy that an exponential decay characteristic function indicates. What remains to be done is we need to design an appropriate type system for which an efficient learning strategy will work that's expressive enough to actually learn tasks effectively. Second thing that we're going to do is our second task for us is to prove that good constraints can be learned effectively. So what we're doing with differentiable types is we're doing a form of constraint learning. So what we want to do is we want to use machine learning to efficiently learn good constraints that allow us to employ divide and conquer search strategies on the program space. And finally, our goal is to design neural networks that are actually capable of doing this efficient constraint learning and this constraint learning that enables efficient program synthesis. And that's the show.
All right. Thank you very much for your presentation. Maybe I can start with my question. Do you have a simple example, a slide or two showing, how a sample program can be encoded and what does it mean to execute it, or, how to use this representation?
Yeah, on a slide, no, but I can show it on the blackboard behind me if you'd like.
Okay. Yeah. Go
Awesome.
on. So let
If you don't
me.
mind, I'm going to switch the microphones. If we mute here,
Yeah, I can do that.
it'll just allow the class to actually hear their questions.
It's
Oh.
okay. Oh,
Is that so Evgeny, can you switch to the
No.
can you see the
You
want to
just,
switch mics?
you just need to mute here, so I unmute there.
Yeah, but like it won't be audible in the Zoom.
All right. You can
I hit mute. Yeah.
All right, test. Okay, also
That's constraints.
there we go. I think that fixed it.
Oh yeah, because it was getting feedback from the microphone.
All right.
Okay.
I think the sound's fixed.
Evgeny, can you hear us?
Yes.
Okay,
I
great.
can hear you.
Wonderful. Okay. So let's go up to our program. And so here, let's take the example of a function. This is a very standard. Our terms are encoded using very standard slot value encoding. So to write a function, we'll write this as a lambda expression. So the lambda expression is going to have a type variable that encodes its type. It's going to have arguments x, and it's going to have a body. The arguments have a very the arguments have a very simple encoding. So
I'll step back.
We have this special symbol for lambda. This is just a standard vector symbol drawn randomly from our set. We have again this special symbol var. We use O times to denote binding. But so the variables then, I'm just going to use a single variable encoding, is I believe just the symbol var plus some special token indicating that it's the value x. or that it's a unique variable here. Then we take the type, which is just going to be sigma to tau as before. So I'll add that later. So we have the body of the function, which is just any arbitrary subterm, not just from this list, but drawn from any of the possible subterms of drawn from any of the possible terms of LLFPL. So it's just any arbitrary term. So I'll add the type. So the type here is going to be this way of doing the composite representation here. So we have this symbol encoding that's a type bound with this chunk encoding, which I'm just going to write as C of a list. So it's going to be kind map type. This is a I'm going off the screen. But this is another chunk encoding of a set that has a domain, which is some type variable C, and a codomain, which is a type variable B, like the opposite. And then the final term is the level, which is some natural number encoding. That concerns the work that Connor did. There isn't really a way to explain it briefly, but we have a number of efficient natural number encodings that are possible in VSA. I'm sure many of the people in this chat have already explored them. So we want to create this lambda expression, right? When we create this lambda expression, we get out a vector. The way these vector representations work is what we have here is in practice kind of a shorthand for each value that we're summing together is going to be a pointer to that value rather than, or is going to involve pointers to values rather than the values themselves, just to make sure that we don't get representational decay in practice, but it's all done. It's all very easy to do transparently. We'll take this type representation and we will cons it with some arguments. We'll construct a list and cons it with some argument, and then we evaluate it in the way that we indicated earlier as a lambda expression by decomposing this vector, i.e. like retrieving its parts and doing string manipulation on the parts.
Okay, I see.
So we
Yeah,
sort
I
of
think
systematically decode these.
yeah, I think I got the idea, but in this case, so my actual question is concerns dimensionality. So if you do this for reasonably small programs, you need very large dimensionalities in order to decompose it into parts from a single vector. So how do you go around it?
So surprisingly, it's not too bad. We do need what we rely on is a large memory. But the dimensionalities are quite reasonable. We do these with 256 dimensional vectors. But the reason why we can do this with 256 dimensional vectors or fewer, because I think I've done it a little bit with 64 dimensional vectors as well, so fairly low even by like HRR standards, um, is 64 is too low. I think the lowest I can really do is 128. But the reason why we can get this so reliably is because what we do is we use pointers, as I was indicating earlier. So we instantiate some random symbols and use an associative memory to encode the relationship between these pointer symbols and the original thing that's supposed to go here. And when we decompose these composite representations, we're going to access the pointer, and similar to like a C pointer, we just retrieve the associated data. This avoids the representational decay associated with like using reasonably small dimensionality, but encoding these like complex representations.
So like another way of putting it is there's kind of a trade-off where you could use larger dimensions, but access cleanup memory less often. Instead, we're getting away with small dimensions, but we have to check cleanup memory pretty frequently.
Yeah, I mean, I think the way that we're currently doing it, we're actually not even like taking full advantage of the dimensionalities that we have. Like we could design representations that demand a lot less lookup. But the simplest way to do it was using these recursive definitions that are very, very reliant on associative memory.
The disadvantage of this is that cleanup memory slows things down considerably, though.
Yes, because we don't have an efficient cleanup memory. Nobody's really solved the problem of building efficient space efficient cleanup memories that are also time efficient to store data in. But that's also an area of active development in our group.
Okay, thank you. I got my answer. So
I hope that made sense.
Yeah, absolutely. So I mean, I still have questions, but I don't want to occupy the channel. So let's see if we have questions from others. So let's see. So I'm still waiting. So sometimes people are.
I'd be happy for more questions.
Yeah, I have a question. So interesting talk. Thank you. So in the intro, you talked about human learning being much more efficient on some tasks. So you got to the point of where you're able to demonstrate that this system can learn in an efficient way, like you were laying out in the intro?
Not even close. This is motivational. That's a very, very long-term project. It's a really hard problem. We're working on it. We have some approaches that we think might work. Yeah, it's what remains to be done is finding the right constraints. This is a first pass. If you read Hutter's work on ICSI and use the like time-bounded and space-bounded variant of ICSI, it winds up having a doubly exponential runtime because you're not just because you are searching through the entire set of possible representations. And then what you're also doing is these are all programs. And in order to test whether any of these representations are any good, you have to run them until they halt or until you run out of time. So obviously this is radically inefficient. It's completely useless. That's why work on ICSI is kind of stalled out and why programs in approach to learning are kind of taking a back seat. What we're trying to do is we're trying to constrain these two parts of the search process. What this language does is it imposes a constraint on runtime. We can guarantee if all the programs that we generate are valid programs of this language, that they will always run in polynomial time. However, the second part of that equation, the sort of outer loop, where we have to evaluate candidate solutions, is still exponential, and we need to impose further constraints that eliminate a lot of candidate solutions from consideration in order to guarantee a polynomial search time overall.
Okay. Is the polynomial search time on the whole program or just some like identifiable steps?
No, so on the whole thing is that we're trying to identify as like the most general scope of programs that we can guarantee is searchable in polynomial time, which is in computer science a hard problem. We probably will not solve the entire problem, but we might find a really general class of programs that can solve a lot of human-like programs problems rather. Like for instance, the ArcAGI task that we can prove is searchable in polynomial time. In this case, we want to search for programs that represent a problem. We can guarantee that entire search will halt in polynomial time. So this is like, this is really like about designing like DSLs to do really, really fast, or heuristically not, but like worst case, really, really fast program synthesis.
Yeah. Okay. Yeah. That's really helpful in understanding what you're trying to do. My question then would be, what motivates that particular choice? Because I would have gone in the opposite direction of saying we want to be able to explore programs that might run in exponential time, but most of the time we want them to run very quickly.
The motivation for looking for guarantees is that the most of the time constraint, that's a heuristic constraint on the search space. It makes our search space relatively large, and it leads to that kind of polynomial decay information gain. So we want to strike really a lot of candidate solutions from consideration in order to use like the kind of like efficient search strategies that are of the same class as like quicksort. Right? Or like divide and conquer approaches over a large search space.
Yeah. Okay. Thank you.
Yeah, no problem.
So let's check if we have anybody to comment or ask questions. I'm very tempted to say, hey, Penty, where is your question?
I'm so sorry. Oh my gosh. I promise we won't do this again. This was a three-part series. I was kind of pushing it with the third one.
Okay. That's yeah.
Maybe I need to rise to the challenge. I'm mainly concerned of the very large memory that could be used in this. I think it'll be a major engineering problem, and I think it'll be solved. I don't want to give any timeline when it'll be solved, but I just cannot see that this kind of system can be made. It could be made to work without a very large sort of random access memory for vectors.
I can give an indication of where the solution might lie for that. Have you read the paper Hop Field Networks is All You Need?
No, I haven't.
It's a really interesting paper. What they do is they show that you can get fast random access storage in a Hopfield like neural network They use a different activation function in the original hop field networks in order to achieve this.
Yeah.
But you can get fast random access storage in a hop field like neural network, where the storage capacity is an exponential function, a reasonable exponential function of the network dimensionality.
That,
So that's doable. Now, the training time that they specify for this network is still really slow because you have to use gradient descent learning to really make it work. So we don't have fast encoding yet, but it's a matter of exploring distinct learning algorithms. It is a really tough problem, but it's an area of very active interest for many competing people in our group.
yeah. Now, what happens to the basins of attraction? Because it's just you have to be able to approach the memory with noisy vectors, and
Yes, yeah.
and so the
No,
basins of attractions, I think that's critical.
yes, it is. So they parameterize the network so that you can have really good, or they parameterize the network in such a way that you can have really good control over the size of your basins of attraction. So you can create them pretty much as big or as small as you want relative to which is going to come into the picture about the stored traces. And you'd want to tune that based on like how separable your or how well separated your data set is. So for nearly orthogonal vectors, which we use for many of these like randomly oriented vectors, which we use for many of these languages, large bases of attraction would be probably fine. For more semantically correlated vectors, which Doug uses for its types, we'd want basins of attraction that are smaller and that are smaller because the vectors are more tightly packed.
I have
That's a parameter.
I have a follow-up question here. So speaking of Hopfield and basis of attraction, I saw the Medicine attended in the beginning of the talk, Medicine Cotered, and he some time ago presented this work on how to encode programs in a Hopfield network. So basically encoding state transition with VSAs. So can you, and somehow it also relates to my first initial question. So, so can you somehow relate, I mean, how this approach is connected to, executing a Hopfield network with like stable basins of attractions?
That's a good question. So I haven't read that paper. Mary, have you?
I don't think I read it either.
I can speculate about how it might be done if that's helpful.
Do send us the paper though.
Yeah. So suppose you have a hop field network with stable basins of attraction. What you're doing is you have an associative memory that's going to encode sort of one-step maps from like one token to the next. So suppose we have a vector representing like a single program state. We can with a hop field network encode depending on what the vector is, we can perform some we can encode like a Turing machine like program table in the hop field network such that there's some corresponding value that's retrieved given some input, and we can continue feeding it like that. So what we do is we program we program that computer, I imagine, or we program that hop field network, I imagine, just by encoding the program table as a set of key value association memory. Actually, I think I didn't, wait, hold on a second. Is that the paper that Dr. Canerva sent me last week? Because I did read that one. Because now
No,
that
it's a implementing finite state machines in the Hopewell.
yeah, I think that actually is the paper from last week. Yeah, so that is exactly what it did. Is it just encoded the program table as key value associations in the Hopfield network memory. So in this case, what we're doing is we're using it's a little bit different in that we're taking an approach that's sort of more similar to lambda calculus. That is, we're using like syntactic decomposition to achieve computation. But we still have a memory that stores all of our encoded functions as a set of key value pairs. It's just that we have a mechanical way to take the retrieved value, and rather than jump to exactly one other state, we can dependently change the program state based on the computation specified by the lambda expression. So we just do a beta reduction defined in the traditional way that you define beta reduction. Is just defined over vector encodings of these recursive strings.
Okay. Okay, thank you. Let me check if we have maybe another question. So we have room for last question. Well, if not, I only want to thank you once again for the great talk.
Okay.
No,
Can I ask one more question?
Yes, absolutely, Tony. I mean, always.
Yeah.
Please.
Yeah, with you. So you were mentioning using pointers to encode larger structure. Are those calculated using, are those pointers constructed using VSA operations, and do they encode similarity, some approximation of similarity of what they point to?
The ones that we use are like they are vectors. They are constructed trivially, so we wanted them to be maximally differentiated so as to avoid representational decay. So they are uncorrelated with what they point to. However, we could just as easily make pointers that have some correlation to what they point to. It's just there's more risk of composite representational decay that way.
Yeah. Okay.
So we'd have to. It's a technical problem that we'd have to solve in order to guarantee that we don't get decay with composite representations.
Yep.
Oh, the benefit of doing that is you potentially would not have to go to cleanup memory as much.
No, we'd still have to go to cleanup memory, but it might be there might be some benefits. I'm not sure entirely what they would be off the top of my head, but I can imagine.
Yeah, you could.
Be some. I mean.
Yeah, you could have some idea of, you could do some computations based on approximately what is this thing pointing to without having to dereference it.
Yeah, presumably. Presumably. Although that does depend, because like the representations that we build are very sort of, the computation is very structure dependent. So it might be really hard to do. But yeah. A lot of hairy problems these kinds of encodings introduce.
Okay.
I had a conversation with a friend of mine who's over at CMU now, who asked me at one point, after explaining this to them, why are VSAs vectors? Why do we need a vector space for this? And I provided an answer that was relatively compelling to me. But they simply would not be convinced because the need for the sort of dual need for like separation in order to get in order to properly take advantage of the structure, but also correlation in order to use the similarity to make some computational shortcuts can be sometimes like competing interests.
Well, I mean, you can use vectors because they provide a good example. But we could also start into the game is just by, I mean, we have these operations and these are these properties, and now you find a space that satisfies those properties, and it doesn't need to be a vector space. It's just it's comfortable to work with something that works, you can make work.
Yeah, I mean, like if you consider, for instance, like string representations, on a like string representations on a computer, though, those are convergently a vector space with most of the properties we care about. They just don't have this bounded representation size that VSAs use.
Eventually, you have to be able to put something into hardware.
Mhm.
Okay,
Mhm.
one more interesting fact. So I mentioned in the beginning that we probably will break the record on attendees, online attendees. So I think I don't know if we really broken the record, but at the peak of attendance, we had like 30 people, so which is really good, really good. So thank you for this as well. So, and thank you for your presentation.
Good
Mhm.
work.
Thank you so much for having us. I hope it was interesting.
Absolutely, absolutely.
Mhm.
Thanks for the great presentation.
Mhm.
So have a great uh, week, and I see you in 2 weeks from now on the next VSA Online.
Yeah,
Have a good day. Bye
take
bye.
care.
All right, thank you for having
Thank
us.
you.